this is part of a 12-part series that we're doing with our webinars here at AWC. These are some of the ones that we've covered so far. We're going to be adding some desalination along with some ion exchange and different resins to this, along with some membrane bioreactors as we move along. And so for those of you that have worked with us before, AWC, we've been around for 40 years. We have over close to 600 plants in operation right now worldwide, with more going out every month. We've got a couple right now that we're commissioning in Florida and Ohio, one in Texas, a few other projects that are going about outside of Canada. All right, give me a second. Let's get more people. Speaking of Canada, good morning, Robin. Robin is logging in from British Columbia, which is pretty sunny there in the Kelowna and the Okanagan region. So this is kind of our manufacturing facility. Everything is manufactured in-house. It's one of the nice ideas of being able to manufacture is that you can actually test everything before it ships out. And of course, everybody's familiar with how we kind of divide our potable wastewater, got our potable wastewater and skid lines. Good morning, Jill. So with that, we're going to pass it over to John. John, if you want to take control of this, and it's all yours.
Yeah. Okay, hang on a sec. Let me get the right page here and
so this is the first time in the series that we're kind of doing this sharing bit. So give us a second while we figure out this whole technology.
Is my screen up there, Alex?
Yeah, we can see it.
Okay. Hey guys, thanks for the opportunity to present our technology here. I'll be speaking about dissolved air flotation, and I see Mike Queso's on from New England there, and he's one of the guys that we work a lot with on dissolved air flotation and big water treatment systems. So, you know, talking 30, 40, 50, well, I guess maybe 100 MLD or 25, 30 MGDs up in his territory. So, but dissolved air flotation's a very unique clarifier in that sense. We've reversing the normal process of settling flocks from either water or wastewater treatment plants to actually floating them to the surface. And it's all about the bubbles, the very, very small micro bubbles attaching to the flock and raising them to the surface to form a mat, which we take off with mechanical skimmers or hydraulically through elevating the level in the tank. Here's a basic picture of our potable water DAF. It shows the main features of it. A key principle is the flocculation at the front, where we're converting dissolved organics and things of that nature to microflocks, and then trying to build them up to something that we can actually trap and float to the surface. It's followed by an inclined plate area there that you see where we switch to the light blue. And that's where the saturator manifolds are, which push the white water, as we call it, or the microbubbles, and it gets mixed and floated to the surface. And the top brown area there is where we have our skimmers to remove that, what we call float, and the polished treated water drops out the bottom and flows into a filter. And there's another system there with that yellow vessel at the bottom. That is the saturator. I'll go into that in a little more detail. But the key is, you know, there is a coagulation step first, then the 30 to 50 micron bubbles, which are electrostatically attached to the flocks and flotation to the surface. Where did it come from? It's been around for a long time. It's was first recognized to float minerals up from finely ground ores, and they even used olive oil as a polymer in those days. So it's a versatile system. We can find flotation in ore or mining processing systems. We can find them in wastewater plants. We can find them in rendering plants for removing solids from the meat packing processes and things. And I'm going to be focusing more on the potable water side, but I will give you a few sort of ideas on where the systems are applied elsewhere. Yeah, so it's been growing for the municipal side. Scandinavia and the United Kingdom were the key sort of areas where it was really developed, and then it migrated over to North America in the 70s. So this is a very interesting picture. This is our pilot DAF, and it's got a plate glass side on it, and that's around 7 or 8 feet long and 4 or 5 feet tall. But it's really interesting. The micro bubbles, they're so small, you actually don't see bubbles. You actually see a cloud or a foam, and it's properly sized. Those micro bubbles are they actually, you'll just see the cloud just kind of slowly rise and leaving the clear water underneath, and in that rising sort of foam, it just completely entraps all the particles and floats them to the surface. And this pilot is very instrumental because we obviously are trying to push as much water through a treatment plant as possible. And so it's very interesting to watch the flow dynamics as we start, increasing from, in this case, 15 GPM to 20 to 25, and watching how the bubbles and the currents sort of flow. Because if we push too hard, you'll find that the bubbles will start to flow down to the bottom of the tank where our launderers are to collect the treated water. That's just part of the sort of the development technology of trying to optimize the treatment plant performance. So this is a bit more complete picture here. I'll shows the skimmer on top. That's where it shows the float and skimmer, and that is generally it's a chain and flight system with the flights going right across the tanks. For our package plants, those tanks would be 10 feet wide. For concrete type DAF systems, which are popular up in the New England area, they'll be 20, 25, sometimes 30 feet wide. There's a couple of different types of skimmers. As I mentioned, there's the chain and flights, and there's also the hydraulic, where they'll just raise the level of that blue water and the top floats out over a weir, taking the float with it. And the saturator at the bottom, what that's showing is a packed bed saturator, so that the blue and yellow sort of diagonal striped lines is actually a plastic media that's very high surface area. So as we take the recycle flow, and you can see that from the clarified water at the far right end, you can see that the recycle pump takes around 8 to 10% of that water, that treated water, puts it back through the saturator, and it trickles down through this high area media where it meets the compressed air, and we get a complete saturation, basically increasing the air, the dissolved air content of that recycled water by, probably 10 times. And it's under pressure now around 65 PSI. And then from the bottom of that tank, that saturated air, it's still not microbubbles, it's just dissolved air in water. It goes through into that bottom of that V-shaped zone. And from there, there's across about every 6 to 8 inches, there's an orifice plate in there. So a very fine orifice which causes an instantaneous, as the flow goes in there at 65 psi, there's an instantaneous, almost explosive expansion of the dissolved air into white water. And it's that white water there that that is blended and mixed with the flocks coming out of that dark green zone. And it's that hydraulics in there where we get complete mixing, and then the fine particles are taken to the surface. Now, what's key about some of the big advantages of DAF on potable water is we very, very seldom need to use polymers. If we have a high TOC going in, we'll use an alum or a ferric coagulant, and we will essentially pull that dissolved organics out and form a pin flock, a very fine flock, which are, not comparable. They're a bunch bigger than the microbubble, but not much. But we don't have to, in a traditional gravity clarifier, to get the density and the settling velocities up. We've got to take this flock zone, add polymer, and try and flocculate these pin flock into a denser flock. You don't have to do that in DAF. DAF just loves the pin flock, and the bubbles will be combined onto it very quickly and floated to the surface. So the DAF clarifier in that sense is very attractive in minimizing chemical costs and handling of those chemicals. It's also very compact. Well, because we don't have to flocculate as much, the flock zones are often quite a bit smaller, anywhere from in potable applications, 10 minutes in warmer water, up to 20 minutes in colder Canadian waters. And another key advantage, so the flock zone is small. The DAF zone is actually very, very small compared to a gravity clarifier. With the settling rate of the flock, it's quite slow compared to the rise rate of the bubbles in the DAF clarifier. And we can actually push these bubble rise rates up to 20, 30 meters an hour. And what that does, as opposed to maybe 5 meters an hour on the settling side, and that ratio is very key, because if I'm floating at 20 meters an hour and only settling at 5 meters an hour, it means my clarifier is a quarter the size of the gravity clarifier. And that means our tanks are incredibly small compared to a gravity clarifier. And it's very interesting when you combine the small flock zone, you combine the small DAF zone, we're able to, in a shippable module, we're able to push out around 2 MGDs of flow, or over 8,000, 9,000 cubic meters per day. So all of a sudden, these packaged modular plants are starting to be service small communities all over the country, and that's a very attractive economic structure, in that this plant can be essentially installed very quickly on a concrete slab with a pre-engineered building, and for very affordable numbers, handle communities of 20,000, 30,000 people. And we've seen a lot of business going our way because of that. So on the saturators, there's a few different ways of doing saturation. There's unpacked saturators where there's no media in it, and that's often used in wastewater because of the biological growth that will happen in wastewater, but they're not as efficient. That high surface area of the media is very efficient to dissolve the air. They can actually be just done with injecting air ahead of the pump, or they could be an inductor where we inject air through a Massey injector after the pump. There's all sorts of ways, but we've actually focused for our potable water applications on the packed bed saturator just because of its significant energy efficiencies over the other methods. And the bubble uniformity is much higher. And what that bubble uniformity does is allows the clarifier to run. Typically our potable water plants, we're running less than 0.3 NTU out of the clarifier when it's properly tuned, and that's pretty standard for many of our plants. And that, at 0.3 NTU, you almost don't need to filter it. You of course need the filtration to meet your the Giardia removal credit requirements, but the filter's not working very hard. It's backwashes are way down. The amount of wastage from backwash water flow is very low. So it's very attractive from an operational perspective to have this extremely clear, low NTU water coming out of the DAF. And, there are other things. There's a broader horizon. You also have dissolved gas flotation units. Sometimes in the oils industry, you can't afford the chance of an explosion where hydrocarbons get it combined with oxygen. So they actually use perhaps nitrogen or some of the volatile gases actually as the flotation air in it. And going a bit further here, here's a picture of some of the different saturators. You can see on the left the packed bed, a very simple diagram, and then the unpacked saturator. The picture in the middle is typically the type of plant we'll provide. It shows the recycle pumps and the saturation vessel, the blue one on the side. So basically 8 to 10% of the flow would be going through, and in the back through that saturator and then reblending. And in the back on those black things behind the blue saturator vessel is the actual compressors that are providing the air. So that is a picture of one of our standard DAF plants there that is in operation. On the far right side, you can see another technique that is used, and we'll use this for wastewater where bubble uniformity isn't quite as essential. The turbidity requirements are not as essential, down to under 1 NTU. We're usually looking at maybe 10 to 20 NTU with a wastewater plant. So we use what's called a saturation pump. It's a cavitation pump, so it's actually is designed to cavitate, and it's that cavitation which will actually dissolve the air into the recycle flow. And not as efficient. Bubble quality is not as good, and we wouldn't use it on a potable water. We probably couldn't use it on a potable water to get the results we achieved. But for wastewater, it's extremely compact. You can compare the simplicity of that saturator pump compared to the packed bed saturator. So it's very attractive to use for wastewater applications. So this is a picture of a plant running up in Halifax. It's already up in Nova Scotia. I'm actually wrong. This one's in New Brunswick. And it shows twin train flocculator DAF units followed by the filters all in one unit. Sorry, in multiple tanks. And that plant there is around 10 MLD or 2.5 MGD. So it was put in a few years ago. This is a very unique application. This is where we are able to do our 10 MLD, including filtration, in one module about 50 feet long by 12 feet wide. And the infilter DAF is unique in that the filter is actually under the DAF. You can see at the very bottom, you'll see the section there with the small vertical black lines, those are actually the backwash and orifices from our plenum, our backwash plenum. And that design, very compact, very high performance in the sense that the overall footprint is very small because we do not have the extended filters as I showed in the last picture. And so if there's a space consideration or a cost consideration that we need to meet, we're probably the one of, I don't know of other people that are doing in-filter DAFs right now, but it's something that if there's an application out there that you bring to us, it's a very good opportunity. Just a little bit about our MBBR DAF. This is it's an MBBR moving bed bioreactor filter, but again, it's very compact. The DAF is compact and the MBBR is compact for wastewater treatment, and we can ship in a single module very high flows and achieve high secondary effluent quality because of that DAF clarifier. This is just a quick picture about when you use DAF. So essentially DAF has for potable water, it has a cutoff point of 150 turbidity units. Above that, we would go with the clarifier, the tube setter clarifier. And at lower turbidity units, we would use the DF direct filter if it's relatively clear water, because we can achieve our log removal credits without the clarifier, or the hybrid AC plant, which has got an upflow granular clarifier followed by a filter, and it's got a wide range of use, but it really can't handle the higher turbidities or the higher algae contents, which is the chlorophyll number that the DAF can. That's where the DAF really excels, is when it's getting into light, fluffy organics and algae. So these are some of the effluent qualities that we're getting. I covered that before, but typically our effluent quality out of the DAF is running around 0.3 NTU and very high color removal. Color and total organic TOC removal. So very good on high organic water, low alkalinity, and lighter turbidities. So this is my last slide. So we've had major successes in our potable water DAF. We happen to be probably the most competitive supplier here in the continent. We've got a lot of installations. The key features are the high capacity with the small footprint, excellent turbidity, color, and TOC removal. So the TOC is important now with the disinfection byproduct requirements. Lower that TOC and the disinfection byproducts will disappear. It's you get the sludge management is very superior. What comes out of a DAF is a 4% sludge, so it's pre-thickened sludge and very low volumes of it. It represents about less than 0.5% of the flow compared to gravity clarifiers, where the sludge is in the 3 to 4% of the flow. Because of its small size, we can retrofit it into existing clarifiers, and that's for communities with a budget constraints or footprint issues. That's very good. We're actually doing a 160 MLD plant in North Hudson in New Jersey. Now we're retrofitting an old wastewater plant to new DAF units, and it's versatile for water and wastewater applications. So that's my quick little presentation on DAF, and if you have any questions, please bring them forward.
Thank you, John. So if anybody has any questions, we have a couple more minutes here you can put them in the drop box. There's a little chat box there on the side. You can punch them in there. I have a question here that came in from Evan. Let's pull it up, Evan. I would ask you to turn on your camera and read to us, but we'll spare you that. So question was, how much space is saved by going to an MBBR DAF instead of a traditional DAF?
That question, the MBBR, like a traditional DAF, wouldn't have the MBBR component if I'm reading this or thinking about the question correctly. The MBBR is an additional module for the biological treatment portion of the wastewater treatment process, and then your DAF. Now, if I say, okay, how much smaller is it than a conventional activated sludge plant and a DAF? Well, where the savings would be is, in fact, it wouldn't work because conventional activated sludge needs a very high RAS flow and returns a lot of sludge. And so you could do it, but it would be a little bit complicated. The MBBR DAF is very well suited because what's coming out of the MBR is just the waste activated sludge, and it represents, if I got 300 BOD going into the plant, I would get about 200 to 300 TSS coming out of the plant. And so that's all the DAF is working on, as opposed to conventional activated sludge, where I might have 2,000 or 3,000 milligrams per liter of sludge coming out of that clarifier. So it wouldn't. So yeah, that's the DAF. The MBBR would be very small compared to the conventional activated sludge, probably a third the size.
Okay, thank you. And so we're here down to we've got 24 minutes in. I promised everybody would try to keep this short and sweet. So I've got two more questions. And so I've got one coming from Brad, which is, what hydraulic capacities are best for AWC's DAF systems?
If you're talking about the flow treatment requirements for potable water, it ranges. We can go from the very small for communities of maybe 300, 500 people, which might be, I'm just quickly, maybe a 50 GPM plant, all the way up to it's really 100, maybe 50 MGD. We'll switch from a modular packaged units to concrete units, and so it's very versatile. And one thing with the package plant, it's so modular. If you need to add capacity, you just add another module. So for a community of 25,000 people that is growing to 30 or 40, we might start off with 3 big modules, and 4 years from now, add a 4th big module. It's a very, very quick expansion.
Okay, and a follow-up question to that, which was similar to that, was what is the max loading cubes per hour with an AWC DAF? Like, is there a very specific size?
Sorry, in cubic meters per hour, you mean capacity of flow?
Yes, that's right.
Yeah, I would say, or are we talking about the loading of the DAF clarifier? Maybe that's the question, like how fast it rises. We range depending on the regulatory applications. Some regulatory groups.
Oh, excuse me. It's meters per hour, not cubes per hour.
Yeah, meters per hour. So that'd be the loading rate. So, in some provinces and states, you're only allowed to go up to 12 meters an hour, and that's where it'll be clamped. Other states, it's wide open. We can go up to 20, 25 meters per hour, and we're playing with different designs now to even push that up to 30 meters an hour. And that 30 meters an hour is about 12 GPM per foot squared.
Okay, and then the last question before we wrap it up from Michael, we have, do you always use a saturator?
The saturator we always use for our potable water plants. It's a packed bed saturator. For the wastewater plants, we will use a saturation pump. It's more affordable. It gets the job done. It's compact, but it doesn't provide us the bubble quality we need to reach the very low NTUs that we get out of our potable plant.
Excellent. Okay. Well, thank you, everyone. I don't know if everybody can see my screen here or not. It should be up there. So thank you, everybody, for coming. We hit our 28-minute mark, so we're right there on time. If you have any questions, you're always welcome to email John or I. We're there for next week. Next Thursday, we're going to be inviting ID Technologies. They're going to have a presentation on desalination. We're going to have a short series, 2 of them on desalination. So make sure you join us. And if you're not already following us on LinkedIn, we've got a pretty active